A particle moves in the xy plane, starting at the origin 0, 0. At each turn, the particle may move in one of two ways. It may move 2 to the right and 1 up. That is, it may be translated by the vector 2, 1. Or it may move 1 to the right and 2 up. That is, it may be translated by the vector 1, 2. What is the closest the particle may come to the point 25, 75? Okay, so yeah, we're moving a particle according to sort of these L-shape moves, and we want to get as close to 25, 75 as possible. So I guess what we could do is say that the coordinates of the point, the coordinates of the particle, let's call it n and m. Okay, n is the number of times moved first way, and m is the number of times moved the second way. Okay, so every time I move the particle right 2 and up 1, that's like that corresponds to n. Every time I move the particle right 1 and up 2, that corresponds to m. So the coordinates of the particle after a certain number of moves, of which n of them are the first type and m are the second type, is going to be 2, 1 times n plus 1, 2 times m, or I could say this is 2n plus m and n plus 2m. Okay, so after all my moves, this is the coordinates of the particle. Now, can we solve the system of equations 2n plus m and n plus 2m are equal to 25 and 75? Obviously, n and m have to be integers. Well, let's multiply the top by 2. And let's do the bottom equation minus the top. Ooh, particle, the moves also have to be positive. So this is interesting. Yeah, this approach might break down. Huh. I mean, this is an indication that shows we can't actually get to this point, 25, 75. Because if we could move not a positive integer number of times, but an arbitrary real number of these translations, the translation of the first type, n, has to be negative. So this doesn't actually get us what we want. I mean, if we thought about this in terms of like, we obviously want more moves of the second type. Well, I shouldn't say obvious, but probably want more moves of the second type. If I do a rough sketch of what we're trying to do, we're trying to get to a point that's at 25, 75, so it's like way up here. And the two ways we can move are either that way or that way. So we're going to want more moves of this type rather than that type. I don't know if there's some kind of sophisticated technique to figure this out, or if I'm just going to... I mean, it looks like there's some sort of remainder thing going on here, right? This is the... in a sense, we're dividing the vector 25, 75. We're trying to divide by both of these vectors and figure out what the remainder is. But I might just try to construct a set of moves that gets us as close as possible. Okay, so what if we take the second move another way of thinking about this. Here's another way of seeing this. Let me redraw this diagram a little bit bigger. So our target is up here. That's 25, 75. We're moving in the second direction as much as possible. So this is parallel to the vector 1, 2. And what I'm going to do here is draw a line through here. Oops. What's going on here? I'll draw a line through this point, which is parallel to the vector 2, 1. And I don't know if it's, I'd have to think about it, but you know, obviously this point will not lie on a grid point, or it won't lie on, it won't be possible to actually land on that line, on that point. But I suppose the closest that we miss that by, this gives us sort of a good guess, a good candidate guess for how close we can get to this point. I also want to make sure that I did this correctly. Okay, so it can move 2 to the right and up 1, or 1 to the right and up 2. So the final coordinate after, and it doesn't matter the ordering that you do this in. So 2n plus m and n plus 2m. Yeah, so I need 2n plus m to equal 25. And n plus 2m to equal 75. Multiply the top equation by 2. Bottom equation minus the top equation. 25, negative 3. Yeah. What would m be in this case? Well, I could do 2n plus m is equal to 25 and multiply this by 2. 2n plus 4m is equal to 150. Again, the bottom minus the top. 3m is equal to 125. M is equal to 125 over 3, which is approximately 41.6. Wait, how does that... I'm confused. Oh, of course, yes. It moves... Wait, m goes up more. I don't see how 41.6 and negative 25 over 3 could get you to this point, right? 41 over 6 takes you way up that way, the m direction. And then you'd be moving in that direction. What did I do wrong? Okay, I'm going to write this in vertical coordinates. 2, 1, n plus 1, 2, m should equal 25, 75. 2n plus m, n plus 2m, 25 equals 75. Oh, right, of course, because this line doesn't go to the left of the point we're interested in. It goes over here. And then we would come back like that, of course. Okay. Whew. This makes more sense. Okay, yeah. I've plotted this properly now, and in fact, you never want to take a step in the first direction, do you? Because once you plot this correctly, you see that the second movement, the direction of the second type of move, is at your target is at a steeper slope. Your target is at a steeper slope than that. So you never want to move in the first direction. you know, if you take moves like this, if as soon as you take a move in the first direction, you're never helping yourself. You're always getting farther away. So what I really need to do is compute the closest point on this line to that point and see how close we can get to that. This honestly might just be faster by brute forcing it, because so if I let m be equal to 25, then we end up at the point P0, 25, which is equal to 25, 50. And in the diagram, you know, now that I draw correctly, there's our target. We've basically gotten to here, directly below it. We might still be able to get closer. You know, we could also, you know, so the distance here is 25. Of course, right? That's a distance of 25. Maybe what I can do here is write the function d as a function of m. So this is 25 minus m squared plus 75 minus 2m squared, square root. That's the distance between the point of the particle and our target. And if I expand this, is it worth expanding this? We can, like, there's probably a closer point. If I do this by process of elimination, right, I've eliminated option A and E. Option D is almost certainly eliminated because I think we can get closer than 25. What is root 53 times 2? It's greater than root 50 times 2, which is 2 times root 2 times 5. Which is also less than 25. Okay, I think, I don't know, we just need to work this out, I guess. What is the easiest way to do this? I mean, I know it's a projection. Goodness. Okay. So I have this point here. I'm going to call that Q. It's kind of like our new target. This will be equal to 2575 dot 21 Okay, if I divide this by root 5 so that it becomes a unit vector, I now have, that's the magnitude, and I have to multiply this by the unit vector. So this is just, that's the magnitude of Q, and the direction is 2, 1 divided by root 5. Okay, so the point Q is 50 plus 75 over 25 in the direction of 2, 1. So that's 2 plus 3 in the direction of 2, 1. So the vector Q, oh shoot, divided by 5, not 25. (10 plus 15 in that direction, so 25 in this direction, 50 comma 25. And that can be reached, this corresponds to m is equal to wait. Oh, no. Oh my goodness. I'm screwing this all up. So Q is equal to the vector. I'm going to use columns. They're more intuitive to me. This dot 1, 2 divided by root 5. That's the magnitude of Q. And we have to move in the direction 1 over root 5, not in the direction of that unit vector. Okay, so Q is equal to 25 plus 150 divided by 5 in the direction 1, 2. So Q is 5 plus 30 in the direction 1, 2. So this is 35 in the direction 1, 2. So m is equal to 35, gets us to the point we want, which is 35, 70. Okay, so now what's the distance between our target and this point? The distance squared is 35 minus 25 squared plus 75 minus 70 squared. So here we have 100 plus 25, 125. Okay, so D is equal to root 125. So that's root 5. Oh, option B. This took much longer than it should have. I mean, the biggest misconception here, I think, that led me down the wrong path was drawing the diagram incorrectly. when I had this point below the line, it completely screwed up my intuition for what was going on. Once you realize that the optimal number of steps to take along this direction vector is 0, then, I mean, you can just do this projection that I have sort of traced out here. Of course, I screwed that up as well. Most people writing this exam at this level probably have these projection formulas memorized. I had to sort of just intuitively figure out what that projection formula was supposed to be. Probably something I should know anyway. But there it is. We got it. And once you figure out what this projected point is, now in general, there's no guarantee that you can actually arrive at that projected point, right? You're taking steps discretely like this. Maybe you jump over it, but at least it gives you a point, a new point to target with this jumping particle. So yeah, there we go. 5 root 5. Pretty sure that's the correct answer, unless I've made some arithmetic mistake somewhere, but I'll highlight it in the video in case there is an error. Thanks for watching.